Okay, so I think the last stream sort of messed up. So basically, just to recap everything and start from all over, this live stream is about me trying to build the RiscV CPU core. Uh, so what is RiscV? RiscV is an open source instruction set. Yep. So this is RiscV. Basically, the processes that you see right now, which is ARM or AMD's some Ryzen processors, they are based off on this instruction set of ARM. So the Intel processor is like based off on ARM, which is like proprietary instruction set. So an instruction set is basically a bunch of instructions that make a CPU work. So RiscV is an open source instruction set. So that means you can make your own instruction set, you can make your own CPU on an FPGA, and you don't have to pay someone for the licensing fees. And also it's like a really good tool for learning. So that's why I have chose this project. So this is the amazing YouTube channel that has done. This guy has done like a CPU project on an FPGA, which is like really amazing. So you build an FPGA all the way from scratch, and it's quite fascinating. So if you head over to his GitHub repository, it's all free. He's made it all free. So I will be referring this repository to sort of try to make my own RiscV CPU core, and hopefully I'm able to do it by end of this live stream. Unfortunately, I don't own the FPGA right now, so what that means is that I won't be able to test it on the actual FPGA. But there are always two parts to things. You first make a synthesis. A synthesis is basically like a thing that it works on your system, and then you put it on an FPGA. So basically FPGA is like a reconfigurable chip that has like bunch of transistors, can make their own circuit, you can say. So that's something for the second part. For this live stream, maybe I build a synthesis of all of this, and most importantly learn about it. So I just want to put it on live stream because I'm too lazy to do this on my own. Maybe with the live stream I might feel like someone's watching me and I will be compelled to do more. I'm just too lazy like that. So let's start with the course. Okay, it seems quite fascinating. So this is the repository. I believe everything is here, and I've watched all his videos. So basically he tells that everything is in here, so let's just go with it. So I've read this part. If you want, you can go through it. So here, first things first, you need to set up. So setup is you install all the necessary tool chains. So it's recommended to have Linux, which I have, thank God. And then for the HDL, you can just use a text editor to write the code in HDL. HDL is like a hardware description code which directly turns into, if you write it in text, it turns into logic. And logic is like transistor gates, or transistors which are formed in form of gates. That's something that you can just chat GPT it and you'll understand. Then there is, for the simulation part, this tool is being used. So the simulation is basically to see if all the things that you write work. Okay, so that's what we are going to check. And then for the test bench, that is the software. So I've installed everything here, and I've also gone to the folder structure to understand it. Maybe I'll visit back and forth, but yeah, so far so good. Let's go with the second step, that is building a basic CPU core. Okay, so this one is quite big. That's what she said. Yes, this is quite big. Anyways, so let's get started with this tutorial. It's a lot of stuff, but yeah, hopefully maybe by end of this day I have something done. If not, we have tomorrow, but tomorrow never comes. Okay, so this is the basic architecture of a CPU. This is what you learn in a course of embedded computer architecture or something like that. In computer architecture, you learn that there is an ALU, there's a register file, there's memory. Okay, so I don't have much. I've forgotten the course that I took, but anyways, I look at some things. They look similar. So let's start ahead. Yeah, so every time you build a CPU, you have to refer an instruction set. So instruction set are basically RISC-V is like reduced instruction set. So there are a bunch of instructions that you can uh, make use of to execute any program. And reduce means there are only few instructions. For example, you can make an entire program of like artificial neural network just by using an addition instruction, right? Here are the instructions that we have. Okay, yep, these are the 40 instructions, and we have to implement all of these onto the CPU core, and then basically you can use it for all the other stuff. So these instructions are something that I learned in the course that I had in my university, but it was like I've forgotten most of them, so it will be a good fresher to start ahead. But yeah, this is a 32-bit core, so that would be more fun to look at. Yeah, 32 bits because you can see the entire instruction is 32 bits. Yeah, so yep, let's read through this. Epic Learn, dude, I will help you, but you can just post a comment on the YouTube video. I'll help you with that. This live stream is more about a RISC-V and how I can make a core. Yeah, basically this is just for my learning purpose. Yeah, but I hope if you tag along, you can also learn something. Okay, so looking at the first instruction, there's like quite a lot of things you need to do. Probably the program counter logic, which should be simple. Then we also need to make an ALU, then data memory and register file. So there's like quite a lot of things at once. Let's see how this is implemented. Okay, so yeah, immediate means that directly it loads into x6 register, whatever value is stored in register x9, and with an offset of -4 is from the address. Okay, so if you take this in hex and you put it in binary, this is the machine code. Am I right? Yeah, FFC48303. Yeah, this is the machine code, so it tells that it's a load word instruction. This is your 6, this is your x9, where is your x? This is x9, this is x6. Okay, an offset of 4, where is that mentioned? Sorry, this is x9, this is x6, this is offset of 4, and this is 2. Okay, let's see how it goes. Yeah. Source register, destination register. Okay, immediate type instruction. Okay, so what do we need? We need all this stuff, right? Yeah, so we need to build all this before we can do any sort of instruction. Okay, so a register file and instruction memory, some data memory too, right? Instruction memory will save all your instructions. I really don't know what SignExt does. ALU, okay. So decoder control unit. This is something that, yeah, this is the decoder control unit. I wonder why do we have to do a logic for this? Why can't we just pass something to the ALU for at the time being? Okay, so let's look at the implementing memory. Yep, that is important. We'll implement some basic piece of memory that can store X amounts of word. It will respond in 1 clock cycle. We'll implement some basic piece of memory that can store X amount of words, and it will respond in 1 clock cycle, which is a way to but this memory is a pain, so currently let's get to work. Okay, we create a memory.sv file in which we write some RTL logic. Okay, I wonder why it is too good to be true. Yeah, I'm not the smartest when it comes to HDL. I'm just gonna let ChatGPT explain me this code line by line. Yeah, this is the module, and then we have a parameter words. Okay, why has this words? Why is this needed? Default contain 64 words. Each of the 32 bits late long. Override this when it's the initial of the module. Ends with the parameter list and starts the port list. Okay. Okay, we declare the ports of the module here. The clock signal. Yes. Okay. Okay, so far what I could understood is this is the module called memory. There's a variable of 64 words. These are the inputs that go to the block and outputs that come out of the block. And the memory is byte address, so it has to be an absolute 32-bit array. Okay, so if the clock is high, begin. If reset is high, make everything 0. Else ensure that the address is aligned to a word boundary. If not, we ignore the right. Okay, so if write enable is high, this is write enable is like a logic. If it is high, that means you write in the memory. So address 120. Sorry, this is yeah, address one. Maybe this is like a check, and address 32 to 1 is the word index. Okay, so the word index is from 32 to 2, and 0 to 1 is sort of like a begin. Sorry, it's like a flag to check, and then you put all this into the right data, right? You put all the stuff that's in the address. So memory of this address, you put it in the right. So you put the right data in this memory variable. We do have a variable, right? Yes. Where is when? Okay, I need to ask. Where have we declared it? Oh yeah, it's here. So it's a memory from 0 to 64. The words are like 64. Yeah, shouldn't it be 64 bits? Okay, yes, I'm not that good at HDL, but yeah, it's good learning so far. Yes. Okay. Okay. You have 64 words in the memory, and each one is 32 bit wide. So it's like a table, and yeah, then you can. Yeah, so this is the read logic. Yeah, let me just check what this means. Okay, so I was wrong. Basically, if this is 0, then your address is a multiple of 4. It's aligned with word. If it's 0, 1, that means your address points somewhere inside a word and not at the start. It's because memory only supports word aligned access, no misaligned right. Okay, it's coming back to that. I've still not understood it quite in depth. Like, I'm not very familiar with this, but yeah, I think it makes sense. Okay, so if you go back to this, you make a module that has 64 words can be stored, each of 32 bits. Then you take your input as a clock, then you take input of the address where you want to write. So this is a 32-bit address, and the write data is what you want to write in it. So basically, yeah, this is the address that where you want to write, and memory is what you want to write. And then there's a logic enable that will tell you if your writing is being done now, and there is a logic reset. So you need reset the memory. I think this is RAM, so you can reset it. It will be a volatile memory. So when you output, you read the data from the memory. So the memory is byte address. There is no support for misaligned write on or reads. Okay, so byte address, that means your initial when you write the okay, we'll talk about that later. So we have a register 31 to 0 memory. Okay, we call a memory array of 32 bits. So this is that, and this is like a memory, like one row of 32 bits, and 0 to words is the vertical, the row that is sort of telling the entire table of 64 bits. So always whenever there is a positive clock edge, the positive rising clock, you begin. So in the reset logic, we check if the reset is 0. Okay, I need to still know what this is. What is B1, B0? Is it like a hex representation? Okay, what is okay, right, 1B0, right? So yes, so if this is 1, if this is 0, sorry, if this is, wait, it should be 0, so it's always high, right? Oh yeah, it is active low. That means it's whenever it's high, that it's not reset. When it's low, then it's reset. So when you give it active low signal, you sort of begin, and then you do everything you put as 0. So for all the entire memory, that is all the 64 memory, you begin, and then you put memory of I for all the 32 bits. You put the binary to 0, yes, and then you end it. Okay, so good. That's good. Yeah, I understood this block very well. Then, if write enable is there, that is, you want to write it. So whatever there is in the address. So address is basically, yeah. So address is the location of the memory, and if the location of in this address, so from 0 to 1, it's a 32-bit address. From 0 to 1, there are like 2 bits. If they are 0, then only you go ahead. Okay, so that address is formatted in here. Address is a word index. So the initial 2 bits are the words index. So if they are 0, that means your address is not misaligned. It's your byte addressed. So it will take byte addresses as in bits of 4. and then you sort of and then you can write the data. Then you can write the data. Okay, so this is clear. I think it will be much more clear later, but this is clear for now. And then you read the logic. So always com. What is always com? Is this like a default parameter? Yeah, what is always com? Okay, always combinational logic automatically infers all the signals using the block, the sensitivity list, right? Yeah, sensitivity list is where you put all the input output. It has the, wait, am I right? Let's see. Unlike always pause, which is sequential, always com is combinational, that is immediately changed. Okay, so it's like a combinational circuit. It's not sequential. Wait, there's the code. Yeah, so yeah, here address 2 is the word index, read data is equal to this. So basically you store whatever is in the address from that space to read data. So from the memory, and in its address that is from 32 to 1 will be the address in the memory. Yeah, that will be in read data. Okay. Yeah, let's read a bit about. Okay, so far this code looks good. Probably understood some of it. Then we'll go ahead with this byte address memory. Okay, so Yeah, so if so load word s3 comma 1 comma 0, what this means is that, yeah, so at the word address 1, you look at whatever is stored here, which with an offset of 0, and you whatever you have here, you store it here, right? Oh, so address 1 into f3, okay. 1 with 0 is 1. So if 1 with 1, if there was 1 here, then it would be at address 2. Yeah, think so. Jesus, my learning skills are absolute, like, bland. I need to make my brain better. Okay, so memory call load word. So load word t1 f comma 5 comma s0. So offset and base. Okay, this is the base address. So 0 is the base address, and how much offset you want is 1. Okay. Oh, so you add from 0 to 1, and address calculation is at the base address 0 to the offset 5. So address is s0 plus 5. Okay, I get it. And t1 holds the data value at the address s0 plus 5. Sheesh. Man, I started at 9:45 and it's 30 minutes and I have one instruction. Let's go. Okay. What is okay? This is byte address memory. The one we learned was a word address memory. So let's learn about byte address memory. Each data byte has a unique address. Okay, each data byte has a unique address. Load stored words or single bytes. Load by those words or single bytes. Load byte LB, store byte SB. Yeah, that was LW and this was SB. So each byte has a unique address. So 32-bit word is equal to 4 bytes. So word address increments by 4. Yeah, each address will be incremented by 4 because it's 4 bytes. Okay, the address of a memory word must not be multiplied by 4. For example, this address of a memory word 2 is 2 cross 4 is equal to 8. The address of the memory word 10 is 10 cross 4. Huh. X10 fourth word in memory. X is third word. Okay, so word 0 is 0, word 1 is 4, word 2 is you multiply by 4, and 3 fourths are 12, which is hex C, and 4 fours are 16 is 4 fours are 16, 16 is hex 10. Yeah. Okay. So far so good. So this is byte address. So basically ensure that address aligned to the word boundary. If not, we ignore the right. So from the address that is this 0 to 1, you check if that's 0. So basically when we check that this thing is 0, that means initial address is 0 and rest of the stuff is the word index. So this is for the address. So in this case, okay, so this is the byte address, word address. Okay, so byte address 0, that means this case. Yeah, if it's this case, then begin. Is that what it's saying? If it's this case, then it's begin. Okay. Oh, Yeah, okay. So if this is always 0, then that would be the case for all these words. If it is misaligned, then it is. Oh yeah, if we try to. Um, yeah, if we try to plot all multiples of 4, the last two are always 0 in binary. So 4 is 100, 8 is 100, and then you add 4 to it, then it's 12, which is also 1100. And then for 16, which is also, yeah, 16 is also like that. It has 0 at the end. So it is aligned. Yeah, it is byte. So this is like a check to see if it is byte address aligned. So if it is aligned with byte addressable memory, then only we proceed, and then we do not proceed. Okay, so yeah, sorry, it took a long time for me, but yeah. Okay, so now the trick here is use byte address memory. Yeah, however, the memory states fairly simple as we do not add support for non-aligned read and writes. We'll add byte and okay, it's half word read and write was at the end of the. Okay, if you're not fully used to while log, sometimes take the time. Okay. Each and every time you implement something, you also test it. Stay there, set them use. Okay, so verification. So when it comes to verifying memory, we'll simply do some writes while tinkering with the write enable flag. It turns out LLMs are bad at digital design and don't recognize special words, so please try to write them. Okay, yes, duly noted. Okay, so this is the test bench. Let's see what this has. Oh, this is pretty amazing that it is in Python. Oh, you can write test benches in Python, whereas your HDL code remains the same. So, yeah, let's get this thing working. Yes, so I have my test bench folder. Let's create a file that will be my memory db.py. Okay, so hope I have my. The heck? Oh, sorry. Okay, so let's understand this code. Yeah. So we make a clock, right? Then we await for a rising edge, maybe. These are the reset things. So first everything is 0 because it's logic low. Yes, that's good. Always 0 after that. So for address in range, wait. I'm just gonna see if there is a template so that I can follow this. Yes, okay, declaring a test. Okay, so this one is to check if the reset is 0. So it's just gonna check if everything is 0. How do I call the module? Yeah, how do I set up the module? Is that mentioned? Because I don't see the module test bench. Okay, in the setup menu. Oh, okay, sorry. Yeah, I need to set up testing. So I need to make module 1, module 2. Alright. So in this module, let's make a makefile, an SV. Okay. Yeah, let's just copy paste this. Okay, so we have the test bench here in the memory, right? It's the same thing. Let's just copy the same code as well. the same one. This is quite different than the one here, right? Oh yeah, it is a bit different. Yeah, it is a bit different. Let's just make the same. Let's just let's just use this thing because we have sort of understood this thing. Let's see if it works. Then we'll try to experiment more. Yeah, so the structure is right, I believe. Yes, I have it set up as per this thing. Each simulation creates a bunch of log and you can get them read by using manually. I don't know how this make things set up. Let's check. Okay, that's fair. Yeah. Yeah, it's probably taken care of, I believe. And this is a lot of work. I really give kudos to the guy who made it. Like this guy, dude, what's his name again? The BRH French Associate General. Like, dude, mad respect, dude. This is a lot of work. Okay, this is new. I'll just refer to his blog. Yeah, this live stream is gonna get really boring because I am learning on the go and I cannot talk on it or explain stuff while I'm learning. So maybe the first one would be like very boring. The second one might have a big higher pace. But yeah, my apologies in advance. Okay, yes, as he has done, there is an SRC folder where we write all the HDL code. Yeah. Now it comes to test it, we make a test bench and we have a makefile. Writing the test bench in Python, we'll see that in a minute. Okay, writing a makefile to tell how to operate test by giving it, yes, some source files, a simulator, we'll use validator, yes, and the other directives. What about validator? Do you have it called here? Is it needed? Yeah, it is needed. So Okay, so maybe it just works. Let me see. Um, okay, so yes. Okay, so we just have to run the make command. So cd and the make command here should be fine. Yes, it is. Okay, goes in. So 34-bit extraction of array requires 6-bit index and not 20 bits index. What is a 30-bit index? This is a 30-bit index, right? Yeah. 6-bit index and not a 30-bit index. Damn, bro. I give up. I mean, I give up as in I want to check it on the LLM. It's a lot easier that way. Is this the end of logical thinking? Nah, but it just gives a better analysis. So let's see what it says. So 64 is represented by only 6 bits, so it's not good. But it should be irrespective of that, right? Because it's in the column number of columns and not rows. Okay, let's just make it really big. So what's 1024? Yeah, let's see if this thing works. Okay, this requires 10 bits and not, yeah, because 2 raised to 10 is this much. So how do we call it? No, but that shouldn't matter as actually, right? Your memory is small, so only 6 bits and your address signal is 32 bit. Taking per variable very strict about indexing, so when you make file one are treated as errors, so simulation compilation stops. How to fix it? Yeah, okay, that's also mentioned in the make file. Okay, I don't know where. I think this is the mode where it says warnings also errors. Okay, so let's see what we can do is use local param for address width. let's see how he did it for his core. Okay, so we take 128 words, right? Basically, I don't see anything. Yeah, this is also pretty okay. Yeah, there's no seem there doesn't seem to be any. What about here? Like, does the test bench has an issue? But this is an issue with the test bench. This is the issue with the test bench. Not with the test bench, but with the actual module. Let's think of any big number that's 30 bits. So what is 2 raised to 30? Damn. This work. Yeah, it's quite. Wait. Yeah, right. It's very huge. It cannot fit. So how do I what if I make this itself low? Let's make it, but we need it to be 32 bits, right? Okay. अरे रुको रुको कैसे हो बात कैसे ओके ओके ले लिया सर हाँ वही मैं थोड़ा लेट हो गया अभी वहाँ पे सॉर्ट करना है फर्नीचर सब धीरे धीरे ले लो ओके मिल गया कोई बेड वेड अभी जमीन पे बिछा हुआ है वो लगा हुआ है प्योर बेड लेना है क्लासेस ढंग से बैठने के लिए अरे ये आपको सेटलिंग में बहुत टाइम लगेगा हाँ थोड़ा बहुत गाड़ी सीखना पड़ता पड़ता अरे और मनोज निकल आ रहे कल आ रहे हाँ नहीं आज आप आज नहीं आज फाइनल हाँ अच्छा before coming for visit यहाँ भाई सही कर रखे हैं हाँ वो अभी उधर पोछा लगा तो सब खुला रखा है वो चल रहा है वो अच्छा पोछा चल रहा है नीचे वाला पोछा चल रहा है Yes, pardon me for that. Yeah, so okay, this is too long. We have to stick with 64. Let's see how we fixed it. And so there's something called memory initialization. Maybe I'm missing that. So you initialize a blank array. And where is it used again? Okay, let's see if this thing works. I don't know why that will work, but let's try. Okay, so yeah, let's go ahead. It's been an hour and a half, and I'm still at one one module, and not even the test bench is ready. But you know what? Let's forget about it. Let's learn. Okay, so you have the initialization as a word. Okay, I'm gonna answer the comments a bit later. Let me get in this zone. So you have memory. Hi, Sean. Uh, nah, this live stream is for no donations. Maybe I could set it up later, yeah, but it's fine. Okay, okay. Okay, the error is still there. That means it's not. Okay, let's just try the chat GPT thing. I'm coming to UT as an exchange student next year. Any advice for me to succeed my thesis? UT is pretty chill. First year is very like you have a lot of courses in the first year. You also have embedded computer architecture. Uh, which also tells you about RiscV instructions. So it's good, I would say. UT is good, and succeed my thesis. Yeah, thesis is highly subjective. So maybe the field that you go in or the professor you select, it will depend more on that. But so far my experience has been good, and such has been as of my friends. So yeah, UT is good, and the education level is same all over the Netherlands. So you don't have to worry about that you're missing out on something. Only thing that you might miss out on is TU Eindhoven has like a lot of university, has like company connects, so it's better in that way compared to UT. But on a bigger picture, I think all of them are same. It doesn't really matter much. Yeah, you just pay less tuition fees in Twente, which is I think is great. So you make a local param for the address bits. So I'm just gonna call this param over here. Yes, in this step, right, where you have issue 49. So no, it's at 49, 41. Yeah, it is. So before this, I will put this part. No, I'll just put it here. Let's see if this works. Yeah, it did. Oh, that's nice. Okay, so we have done our first test bench, which is passing. That is great. Yeah, so let's now figure out why it's working because um, yeah, I just ran this, so let's see why is it working. Let's understand the test bench. So first things first is you have this part. Okay. Yeah, you have how do I Yeah, so the first thing is you make a test bench to check if the the thing is reset. So this comes under that. So first thing is you do the reset thing. So for address of you reset everything as 0, and then you set the device under test. So this is the part where you send information. You send you give the clock. Send reset signal to module, and then it will just do its stuff. So you first put the rising clock. Oh wait, I don't know what this means. Maybe it's like a 1 clock, and then you do this, and then for all the address in range of the words is the 64 words. So dot.words.value. Uh, yeah, I think it just means this value, like just take the value part of the words. Then design interface dot address dot value is equal to address. Okay. Yeah, for each address, you take each address, and then you await the timer. So it's gonna start as, yeah. Why does it like don't have to tell that? Oh yeah, like I'm checking every word address. Sorry, I'm checking every byte address. So it should be multiples of 4. So maybe that if I just remove this, what if it does it? It might not work because I'm just checking everything. Let's see if that thing works. Okay, it is still passing. Yeah, how would I test this? Maybe we'll check it in the writing step. Yeah, we'll check it in the writing step. So this is reset part. Then test, write and read the data back. So you write dead beef, cafe babe, 1 2 3 4. Okay, all these things you check. So for address data in test data. So design address dot value. Okay, so this is the address that is 04812. I don't know how this, yeah, for address comma data in test data. So this is your address comma data. So dut address dot value is equal to address. So for this address and this data, write enable 1 rising step and write enable 0. So that means you put this data in the memory, and then you wait for this. Yeah, so far we are just working with the memory. Yeah, I'm not need to work about. We're just testing if the memory is able to store, reset, and just read. We can read from the memory. So disable write after 1 cycle. So dut write dot enable 0. Okay, verify the write by reading back. Okay, write the multiple addresses. So for I in the range 40,4, dut address value, 40,4 just like a random write and disable write and read back values to check. Okay, so write enable dot value for now in the range, disable write and read values back. What if, I think if you just interchange this, it won't work, right? If this works, then there is something wrong with everything. What? Give me a second. There should be something printing, right? Why isn't it? There's no printing. Yeah, there should be something getting printed. Yeah, but there's a if else test, like, there is no statement to check it, right? Is there something else later? Okay, assert is the comparison thing. Let's just put not equal to see if this thing still passes. Okay, what is this? Okay, better yet, let's start with a simple, very vanilla example. So maybe I'll start with just reset first and then work on these things. So let me just comment these out, and yeah, I need to know what is meant by assert. Oh yes, it failed. That's good. Okay, yes, that means our reset is something getting failed. Yeah. Okay, so the reset is something that we can verify. Assert is a let's just understand this from ChatGPT. Okay, so yes, that seems good. Alright, assert command just compares this condition, and if there's an error, it's going to print that it does not reset. And the await timer, what does the await timer do? Yeah, await timer. Yes, just a second. Await waits for the first rising check. So, but this is for checking for the first rising check, first rising clock. What does this do? Pauses the execution for a specific amount of simulation time. Okay, so it pauses this thing. Right. So let's do something. Let's write our own test bench for the same this thing, for the same data set. Yeah. So let's use the same thing. Let's write our own test bench for this. So for yeah, there are two things. So one is your address and this. So for address, comma data in test data. Damn, AI is so useful. No, I'm gonna write my own. Okay, so first things first is you need to put the data onto the address onto the module. So you need to call the object that is designed under test, and in that under test you have to call the address. Okay. Sorry, the design under test has these variables. So you can see that it has address, right, data, label. So we need to check if we just want to write stuff, right? So for design under test address, we have to keep the address at 0, and we need to put that value there. So address dot value equal to add, yeah, and then design under test. One is the address, and then the test data you need to also put. So I would say yeah. So what's it called again here? It's called write data, which is the data that is to be written. So I would type yeah. Okay, and then you would have the design and the test where you have to make the write enable value equal to 1. I think this is it. We don't need to wait, and then we need to yeah, once we write yeah, let's just not give it a signal. Let's do something not the AI is suggesting. Okay, and then yeah, once I wrote like for all, I need to check if what I wrote is correct. So I'm just gonna write that assert dut dot no, I want to check if whatever I wrote on the particular memory is same. So first you write everything, right? This means you have written everything onto the module, onto your memory, and after writing it, I want to check if it is correct. So to check if it is correct, I would have to write. I'm so hungry right now. I'm gonna get something. Yeah, so basically I've written like this for loop will write everything onto the memory, and after writing stuff in the memory, I need to check if it's the same thing. So I just write a comparison block here. okay, let's just do this thing and just comment it, and then I want to compare. So dut dot data dot value is equal to assert. So we have to write assert dut data dot value is equal to test data can this be like 1 or 0 or something? Let's see. Yeah, how do I compare the stuff? So I basically write yeah, how do I check it? Let's just refer this thing. Okay, so we need to make the write enable 0. Yeah, because we are not writing afterwards. Huh. Okay, so this is like waiting for each clock, and then you sort of make it. No, this is for all the values, right? Yeah, this seems like it's for the all values. Disable write after 1 cycle. Dut dot write enable dot value equal to 0. Verify the write by reading back. So dut dot address dot value is equal to address. Yeah, how do I read stuff? If I just put this, like assert. Yeah, right. Read value equal to data. Yeah, why do I need to know the address? Like, why do I have to put the address of the data? Yeah, because every time you put the address, and based on that address, you're reading, right? Like, for example, of this read for this address, you put the address and then you read. I think this will return us an error, but let's see. Okay, this thing has passed. That is weird. That means the address is actually, yeah, it's coming in. has he written the address here? Is it something necessary? Because you're doing it in the same for loop, I imagine, and I don't think this is necessary then, because you already have the address value here. So once you do that, you disable the write and then you check it, and then you see if it's okay. Now let's do one thing is, let's write if head is equal to 12. Yeah, let's just wait for this, and then okay, let's not wait. Let's test something where we increase the test datas. How do I change the index of like test data, like 12, right? 12. Yeah, how the heck do I think maybe ChatGPT can help me. Yeah, I'll just fix this one. Oh, by the way, like, that's what my friends were saying. Softcore is basically the softcore of RiscV. It is not something else. So, yeah, yeah, my history is out there, but the softcore I'm talking about is the RiscV softcore, which is like softcore on an FPGA. It's not a softcore on the, you know what I mean. Yeah. Okay. Yeah. So, yeah. So just check. Yep. So I'm manipulating the data. Then also it's no. I want to manipulate it after this. Yeah. So after this thing, right? Okay. What's the error? Yes, so it's failing at this for address 12, which is great, which is great. So now we have sort of understood to check if read write is working. That's great. Uh, yeah, we have understood it fully. Okay, so this is good. Then let's go to the other step. That is, we will check it for multiple, like reading and writing for multiple range. Yeah, it's pretty much the same thing. I guess I can delete this. So that means the test bench is passing, which is good. Your memory is good. Um, yeah, so hooray, we have done one module, and yeah, this is one module is done. And if, I hope if I just comment this. So, yeah, so that means all this is okay, and writing into the address, then read back for I. Okay, yeah. I think I need something to eat, so I'm gonna take a break, probably 10 minutes. Yes, I am back. Okay. Yeah, this is not the ideal food, but I don't have time to cook. I might cook later. Okay. Yeah, so sorry, we are done with the first module. Let's look at what other modules we have to do. Yeah, sorry. Yeah, so there are quite a bit of modules. There's ALU, then there's a control unit for the ALU. This is the entire CPU where everything is connected together, if I believe. Yeah, okay. So we have just done one, that is the memory. I hope other stuff might be a bit easier, but let's try doing it. Okay, so for the memory, I was thinking, so already there is a working code from this guy. Oh, I believe there is a different one for the FPGA. Yeah, so in the actual course, there's an FPGA edition, which has like a different. Yeah, this has a lot of stuff. Dude, this is insane. Like this guy, like really kudos to this guy. This is actually insane. Okay, long way to go, I guess. So the FPGA version is a bit intense. Let's do the single cycle version. Let's get used to what stuff is there and everything, and then hopefully we can scale it up. So yeah, so for the memory thing, we figured that out. But I think the memory that is done in it's given an example. The code for the memory is not the same as the one that was there. So let me go to this. Yeah, so this, oh, okay, there was not much difference. Um, yeah, this for the write operation. Why is this going twice? It's the same thing, right? Oh no, sorry. This is for the reset. Begin, and we just do it twice just for safety, I guess. Wait. And then, and okay, and else begin. If that's not the case, then if write enable is there, yeah, if we just check if misalign this, yeah, this is good, and else begin. So for okay, so this is something new, that is byte enable. This is something new, because earlier in this thing, you just take the memory and you just store it, you write the data onto this, but what's happening here is that you yeah, so within that word you selectively look for write bytes. Yeah, I sort of have an intuition, but I'm not sure if it's right. So basically, you have a word which has 4 bytes. So in those 4 bytes, you just check if it is for each byte. So you are writing on the word as well as you are writing on the byte. And here is the thing: why are you multiplying it by 8? Yeah, let's ask ChatGPT. Oh, okay. I believe there is also a byte enable. Yeah, so there's a write data, there's a write enable, and there's a byte enable. So this is for writing specifically to the bytes, and I believe the code is also pretty simple. Okay, let's go some corresponds to, okay, so if we want to write a byte, if byte enable, so it is going from 0 to 4. So if it is only for that particular byte enable number, like this is goes from 0 to 3. So if it is byte enable is that number, like byte enable this, like byte enable whichever number is like 1 among that 4 bits, that will have the modification going on, and here the I is chosen such that, oh, then you sort of select the 1 byte. So this logic is that, okay, I get it. Select 8 bits from write data, 8 bits to okay, so this is for the byte specific operation, right? Let's just copy this now because this is more interesting to me, because you also do the writing at the byte level, but for now let's not think about it, because for now we're just learning. Maybe in the future, but let's just keep it as a point that you can modify the byte. So okay, so far so good. And now I'm back to the verification. Okay, so we have done the first module, that is the memory. Now let's do what the register file does. So for the register file, it's just, yeah, a register is basically a storage element. It's like a variable you can think of. And we need 32 cross 32 bit registers. We'll implement it like memory. Yeah, but the file fixed size is fixed to 32 bits with 5 bits addressing. Okay, the IOs are a bit different ways we have to accommodate the instruction types. For example, in R types, which operates only on registers, we can write a register while getting data from two of them at the same time. Okay, I don't know what that means, but so if you look at the code, you have a module, you have clock reset, yes, you have address 1, address 2, then you read data 1, data 2. So address 1 and address 2 are both 8 bits. Like sorry, one is 4 bits, and this is like data. Oh yeah, sorry. So 5 bits for the 5 bits for which register it is, like the address register's address, and the data is 32 bits. And for the write enable and the logic write data for the logic address. Okay. So 32-bit register, 32 of them addressed with 5 bits. Yeah, so this is like a matrix of 32 cross 32 registers of 32 bits. Right logic, if the clock is high and the reset is high, then you make everything 0. Like all the 32 bits you make 0 for all the registers, and else if the write enable equal to 1. Yeah, so if the write enable is high and address 3 is not equal to 0. So what is address 3? Have we declared it? Yeah, what the heck is address 3? And address 3 is not equal to 0. Begin register's address 3 is write data. Yeah, I don't quite know what address 3 is. Maybe it's like a storage element. Yeah, it is a storage variable. Okay, I get it. So it's like a storage element and it's always 0. Everything is 0 in that. Then registers at address 3 will have in the right data. Okay, I think I need to know what registers are. Maybe I go to this playlist and understand it. So this is introduction. This file registers. Hey, yeah, is that the case? Um, it could be either your issue because maybe one of your earphones not connected, or I think it could be mine. I'm not really sure. Um, yeah, this is like a testing. Like, please pardon if that's the case. I'm sorry. The video I'm playing is streamed to my headphones. Uh, yeah, I don't really know how to fix this. If I play this, the video is gonna mess up the audio, and it should be fine. Let's see if I can make this work. Um, yeah, I don't know how we can fix that. Just give me a minute. I think I think this should be fine, right? I think you can hear the audio now. Okay. Yeah, I'm using OBS. Yes. Yeah, I'm glad you can hear it now. Yeah. Amazing, amazing. Okay.
and we see some arguments with names like how they are used. The register x0 has the alternate name of simply 0. This register is particularly interesting because it's the only one that is not general purpose. It's treated specially by the hardware, and in particular, it's hardwired to always contain the value 0. This register can be used as a source register in any instruction where you want the value 0, which is often quite useful, and it can also be used in instructions as the destination register when you don't want the result, in which case the result of the instruction is simply discarded. The next register to look at is the return address register. The alternate name is simply RA, and this is used for call and return instructions. With RISC-V, the call instruction does not actually push the return address onto an in-memory stack. Instead, what it does is it saves.
Okay, so long story short, we need to implement all the register. So here, this is a register file. So I think maybe, yeah, to accommodate all this, for example, in our page. So I think this one is just an example. If I look at the, let's see the actual implementation. Okay, here also there are two, but why there are two? There should have been a lot, right? Check the FPGA version. Okay, I am confused. I'm gonna ask ChatGPT. Okay, so this is for, so where is the register file? There should be a register file, right? Where are the registers? Is it in CPU? Okay, so basically it's not the register file with all the registers explicitly mentioned. It's more like a way to read registers and write it into registers. Yeah, maybe we can experiment with that. Okay, so Yeah, because we need two registers at once because we sometimes use two registers to perform an operation. Maybe because of that. I believe it's mentioned. Is it, okay, so let's do the. I believe that is all set up. The Yeah, let's just go through it once again. You have a module, you have the input signals that is clock, reset, and then you have the logic. So you need two registers for taking in the input, and for output you just use. Okay, so these two are the addresses of those registers, and output is the data that you keep in those registers. So you handle two at a time, whereas for writing, for writing, I'm just gonna get this code experiment. So there are 32 error registers, and we can give them address based on 2 raised to 5. Yeah, so you have a binary 5 digits to represent the register address. Okay, that's clear. And then read data to output of the selected registers. So read data is 32 bits, so each one has 32 bits. So write enable for writing. We can read two registers at once, but for writing, we can write one register as per this code. And address 3 is the right address of the it's the right address of the register. I see why address 3 is mentioned now. This is an actual register file. Okay. Index into this array, perfect. Yeah, so first if reset everything is, you make everything 0, yeah, and for the write operation, reserved for 0 constant according to this spec. So else if write enable equal to 1 and address 3 equal to 0. Address 3 is basically your this is right address, so that is 0. That means you're not writing, you are just it's not equal to 0, that means you are writing on it, right? And you write on this register. Yeah, you just write on this address since it's enabled. Like if it's any address which is okay. So but what if it's like continuous 0? I think we don't. The first register always is something different, right? The first register is always a 0 register. Yeah, it's always 0. Yeah, the first register is always 0, and this is your pointer. Program counter is also a register, I believe. Okay, we'll see about that later. We don't need to worry about that. But so far we know that the first register is always 0. That's why in the code also you mentioned that it's not equal to 0, because that will be the first register. You cannot, it's a fixed register, you cannot do anything to it, so we keep it at 0. That's good. So begin register is equal to registers 3 less than equal to write data. Okay, and end. Yeah. So RiscV specified x0 is always 0, you cannot write to it. Yeah. Write data into the selected register. Okay, so writing happens on the clock edge, typical of the synchronous design. And in the read logic, you just read it. Okay, so this is pretty clear to me. Yeah, this is pretty clear to me. So let's just do it again and have the test bench thing working. So for the register file, you have the clock, the reset, two addresses from which you can read. So two read ports, yeah, that's good. Because this could be in place of any address was for selecting the address. Read data that you store the data from the register into this particular variable, which is 32-bit. And then for writing, you just write in one register. So this write enable is a flag, and write data and address 3 is the address of that register where you want to write to. So this is your entire register block, like the entire register table. So it's a 32 cross 32. And here the first register is fixed register, that is 0, that we saw. So this is for resetting all the registers. If it reset is that, then just make this reset. So every time we put this condition, so every time the clock is high, we check if the reset was also high, and if it is high, if it's logically high, here it's an active low signal, then you put it as the thing is 0, and write except on 0, reserved for 0, constant according to this first step. So here basically we are writing the data into the register, and we have to confirm that it's not the 0 register, because all the other registers are some other registers, and only this is a fixed 0 register, okay, as per RiscV. Okay, so that's good. We are done with this, and then we begin, and then there is an always combination, begin read logic, read data 1, registers. Okay, yeah, this is just to read the registers. So far so good. Let's go to the test bench, see if it's alright. Okay, so here we declare, I see there's numpy, which is good. And then we have, one thing I'm really amazed is maybe I can put something, like if I want to test actual hardware logic, maybe I can just put it in Python, where I can process my webcam feed and also have a test bench on the register. So maybe I develop on the same RiscV code to put like a hardware accelerator for AI, or like the possibilities are really fun. I mean, maybe I could do a lot of projects, because on the test bench, but I'm not sure how it will link. But yeah, let's look at this thing first. Okay, so you have a register file test. You start your clock, you set everything reset 0, and you make the reset thing. Okay, feel local state of registers of all 0s. So theoretical state, okay, 0 for the nice. So loop in write and read values for So he has made like some registers on the file. So I think you have to set the first register as 0. Yeah, all are 0, it doesn't matter. So generate a random register address. So from 1 to 32, skip 0. Yeah, you skip 0, you make random addresses. But this has to be in, I believe this has to be 5 bits. Yeah, so this has to be 5 bits, right? Why is it 31 bits? Oh, okay. So it just gives a random number between 1 to 31, and that number is like a 2 raised to 5 number, right? And that 2 raised to 5 number, we can use it for storing the address. Okay, that makes sense. And then you write value is equal to random minute from 0 to, okay, so it could be any value. So these are your declarations for the first thing. So it is a random register at first, right? And for the first timer, you put the address value 1, address value 2 is this, okay, good. Then you read value from this, so read value of theoretical addresses from this range, okay, so you read from the file, and if this value is in the file, that means it is okay, it is passed. Then you put the address 3's value, so the address 3's value is address 3, then you write label 1, then you write data into the right value, so it's also a random value, and then you make it 0, and then theoretical results is equal to right value. Wait, but how do you check it? Like here you check it, right? Then you need to check if you confirm it. Maybe confirmation is not done here, so let's do that. I think so. But oh wow, failed. Did I do something? Okay. Okay, this is not a problem. But right value is declared here, right? It's a random. Let's just make it from 0 to 0 fs. Maybe this should be like. Is it 1, 2, 3, 4, 5, 6, 7, 8? How come I did add value? It's like a random number, right? Okay, let's just copy this. Okay, the error is that in 51 here there is an error that write data is equal to write value. Oh right, sorry. That explains it. Let me just make this as it is. Okay, this is a bit confusing now because I did add dot value, but it's still not considering it. Yeah, but I did add dot value. Where did I miss it again? Oh, pardon me. Yeah, I don't know what is wrong now. But I have changed it, right? It's like right here. I have saved this. Okay, why is this not happening? Let's do some other. Okay, maybe it's checking an old file, but all the dot value have been set, so ideally this should be correct, right? What does ChatGPT have to say? No, I did add this for all the inputs. Okay. Oh, um, I think the naming is incorrect. RegFile test. Oh, I actually. Um, do to clean it outside, I guess. Okay, this is quite funny. Okay, where is this thing now? It's oh god. Um oh god, this is so fucking stupid of me. Oh shit. I am changing it in the other file. That is so stupid. That is so stupid. And it took me so long. Dumb. Okay, anyways, so we are in the reg file. Here's the test reg file, and I think we are to, yeah. So dot value should fix this. Yeah, so this should just fix it. Okay, great. So we have tested the register file. So yeah, that is out of the way. And now, okay, so we have done two modules. Can we do one instruction set by the end of today? So yeah, for the load word, we need with the register file, we need an instruction memory. We need some memory too. So we first did the memory thing, that's okay, and then we did the register file, which is also okay. After verifying the test bench, is also quite good. Although I'm not fluent with making my own test bench, but for starting, I feel it's good. I will be comfortable if I put more time with it. I will be comfortable in making my own test bench. So for the arithmetic logic unit, okay, so this is something that what stack am I using? For what? Which stack do you mean? For this, right? Okay. So it's not exactly a stack. Basically, let me open the setup. So in the setup, if you see that you use Linux, and in the Linux, there is a simulation tool which is called Verilator. This is basically an open source tool where you can simulate your hardware level synthesis code before you put it on the chip. Like before you put it on the FPGA, you can test some things on here. So think of this as something that verifies what you. It's like a compiler for hardware language, like high level synthesis language. It's think of it as a compiler. So that is being used, and the other thing is this. This is a cool thing that I just found out, is CocoDB. So basically, what this is like a test bench to verify your hardware, and it also lets you work with Python. So you put your Python stuff, like you use a Python like I'm using a Python, like I'm in a Python environment. You pip install CocoDB, and then and then you can write the test bench in Python, which is way more convenient. And you organize it in a such a way that let me show you. Yeah, you organize it in this way, such that your source will contain the hard HDL language, and your test bench will consist of the Python code, and you have to make a make file. So the make file is sort of connecting the logic and also this test code. So which is good, because if you want to make a test bench, it's like a C++ code sometimes, or it's like a weird code. It's a hardware sort of code, so it gets very annoying. But this is very convenient. Like I wish I knew this earlier. But this is very nice, I would say. So you just use Python. Like think of also, maybe you can also integrate your video feed in OpenCV to do it, which I think should be possible. So if I ask, we use OpenCV tools in the Coco TV test bench Okay, so this is also good because it's in Python. It's like it would be quite good to just test your workflow or hardware thing there. So if you come look at the stack, it's basically you have a Linux environment, then you have ventilator, then you have CocoDB for the test bench, and yeah, that's pretty much it. And this is how your structure is. So this is how your structure is, and then finally you make a CPU file. This CPU file will connect all the modules together, and then this will be a top level entity file, and you just have to build this or just flash this or something, and then you're done. This is quite good, and this is really interesting. He left a really nice comment. Yeah, so yeah, that's the stack that is being used here. Okay, so carrying forward, let's go to, so we tested our register, we tested our instruction memory, and what else do we need to do now? Yeah, we need to implement the ALU, and after the ALU, we have to implement the sign extender. Okay, the sign extender, then a basic controller. I think this would be another, like a very simple controller, I think, for load word. Yeah, okay, and okay, this would be a lot of learning curve for this, and then you make your, okay, so this will be very fascinating. So we make a LW, like load word data path. Basically, for the load word instruction, we need to figure out all the things that are, all the modules that are there, we have to connect them, which is quite interesting. Okay, this one is fun. This one would be fun. Then you do the stored word, okay. Sign extender. Whoa, there's a lot of stuff. There's seriously a lot of stuff. Okay, there's a lot of stuff. Yeah, I appreciate it, man. No worries. Okay, so far so good. I believe for the next thing, I'll be able to take a better speed up. So before we go to the ALU, I'm just gonna take a small break, and then I'm gonna start soon. So probably more 20 to 30 minutes. Yeah, I'm gonna take a small break. It's also quite cold. Yes, I'm back. Had to cook a meal because I was kind of hungry, so this is what I made. Hopefully it tastes good. It's always a bet. Okay, anyways, for the next thing that we need to implement the ALU. Yeah, so the ones who are asking the questions, I'm trying to do a RiscV CPU. First step is the synthesis part, and then I would preferably put it on an FPGA. So I refer this project from a guy on YouTube. So this is his channel. Yeah. So yeah, so I'm following this course that he has done. So far it's been really good. So for now I've implemented the memory and then the register file, and now I need to do the ALU, and after the ALU the sandwich. So the ALU seems pretty easy, so let's work on that. Yeah. So first things first is you need you'll probably go to VS Code. Yeah. So for the module there are a couple of inputs. Yeah, I really need to know how an ALU works. Yeah, it's better to do that. But it's like pretty simple, I guess. You do the multiplication, addition. Yeah, this add, and, or, subtraction. Now I'm just gonna see the video so that yeah, let's just see what an ALU is.
Welcome to another video in a series in which I describe the RiscV core, and there's
Oh. Okay, I think I'm audible now.
the RV.
Yeah, just a second. Yeah, I'm not sure if you heard me last time, but what I was trying to say is I'm trying to make a RiscV CPU in Verilog, sorry, HDL, and yeah, I'm just referring this documentation that is made by this channel. So it's a really good. He has implemented a RISC-V CPU 32-bit on an FPGA. So he's made a he's made a documentation which is quite interesting. So I thought I'll try. And yeah, this is the live stream about it. Yeah. So now we're jumping into the ALU. So let's see a bit of series on how it actually works. So yeah.
32 and the RV64, a machine instruction. There could be other things in the opcode field. For example, we might see a pseudo instruction, such as the call instruction, and we'll talk about pseudo instructions later. This video does not discuss compressed instructions, but we might see compressed instructions. Those all begin with C and a period. And finally, we might see an assembly directive, and those all begin with a period. And here's an example of an assembler directive. There are actually two styles of comments. The first one begins with a pound sign and runs to the end of line, and that's all we've seen so far. And that's very typically used to describe individual instructions, as we see here. The other style is with the slash and asterisks, as you have in C, and these comments can span multiple lines, and they're particularly useful for removing code which you don't want to be included, and also for large blocks of comments that describe entire functions and so on. The line might also begin with a label, which is an identifier, followed by a colon. The colon is not part of the label, but it's necessary to identify that this thing is a label, and not, say, an opcode of some sort. The label itself is an identifier containing letters, underscores, and it might even begin with an underscore. Some assemblers have additional syntax. For example, it might involve periods and so on. The label is essentially a symbolic name for some value, and that value is the address of the next thing that occurs, and in this case, it's the add instruction itself. So if it's on the same line as an opcode, as you see in this example, it's the address of that instruction. If it's on the same line as some assembly directive, such as a 5-word directive.
Hey, I see that BMQ. Yeah. So did you hear my answer or? Yeah. So basically, I'm trying to build a RISC-V a CPU core using HDL. So RiscV is an open source instruction set which you can use to build your own CPU. You cannot build on ARM because ARM is an instruction set that is proprietary to pay licensing fees. So RiscV is an open source and I'm just trying to do it for learning purposes. So in this video I'm trying to build that. So right now I'm trying to understand what the ALU is. I have a brief idea about it, but it's good to revisit, right?
That define a data item, well, it's the address in which that item is placed in memory. We can also have labels that occur alone on a line by themselves, in which case it's the address of the next thing that occurs in the file, which is presumably an instruction or some data. After the opcode, we have 0 or more operands, and if we have more than one, they would be separated by commas. These operands can be either registers, as we see in this example, or they can be immediate values. Now, in
oh shit, you cannot hear me? Hello, am I audible now? Is it audible now? Okay, and I also realize I have yeah, let me fix it. Yeah, I think there's something issue with my mic because I can also hear me in only the left speaker. Yeah, something is up. Instruction set which you can use to build. So RiscV is an open source and I'm just trying to do it for learning purposes. something is up. I don't know now, but is it better now? When I said instruction set which you can use to build so for learning purposes. Yeah, something's up. I don't know now, but is it better now? Yeah, I think the audio should be better now. Yeah, so let's carry on with ALU. Okay, good.
Using both an immediate value, and so pseudo instructions would index.
Thank you, man. Thank you so much.
Immediate value, and that immediate value is limited to 12 bits, so it has a limited range. The value is sign extended, so the range is minus 2k to plus 2k. So this gives you pretty much all the information you need for these two instructions. I do want to point out that for the RV32, this is a 32-bit addition because the registers have 32 bits, but for the RV64 standard, the registers have 64 bits, so these would be 64-bit additions. Another thing to ask is how are these two instructions encoded into binary? Now I'm not going to show the encoding for all the RiscV instructions, but I want to show these two to give you an idea. In the case of register-to-register instructions, we have an encoding that looks like this. So we see that we've got 5-bit fields for the various registers, right? 5 bits is enough because 2 to the 5th is 32, and we have 32 general-purpose registers. The opcode is shown in the bits that are colored brown, and you can see that the opcodes for these two instructions are almost identical, but not quite. And in the case of the add immediate instruction, we've got a field, shown in blue, that is 12 bits for the immediate value, and this would be sign extended to give us something in the 4K range. The other register-to-register instructions and register-to-immediate instructions are encoded similarly, but the opcodes are different. Here are all of the RiscV arithmetic and logic instructions using the register-to-register format. So you can see that both operands are coming from registers, and the result is being placed in a register. So we have addition and subtraction, and then we have the logical operations AND, OR, and exclusive OR. These are bitwise operations. So for example, with the AND instruction, each bit of RS1 is logically added with a corresponding bit of RS2, with the result being placed in the corresponding bit of register RD. We've also got 3 shift instructions, shift left logical, shift right logical, and shift right arithmetic. The shift amount is coming from RS2. And with the logical shifts, we put zeros into the vacated bit positions. And with the shift right arithmetic, we place the sign bit, or we duplicate the sign bit into all of the vacated bits in RS1. So shifting left can also be used for
okay, that's enough. Okay, so you have source register 1, source register 2, and these are your inputs, and the output would be the ALU's result. So ALU is like an arithmetic unit between 2 registers, right? And this is the ALU result that you use somewhere. So SRC1 is the source register 1, source register 2, source 1, source 2, right? And ALU control is basically your 4 bits telling you whether you want to do addition. Then so based on ALU control, you do your addition, subtraction, whatever. So let me see how that thing is. So ALU add, the first instruction is ALU add, I believe. So that is 000 is add, 001 is and 002 like so the binary 0010 is like or something like that. Let me just confirm, but I believe it should be the case. That's the case operator. I hope ChatGPT knows more about it. Okay, yeah. So that's something called as a package file. I don't know how this is structured, but this is like a config file that you take a reference to. So as we saw earlier in the ALU file and the package file, so this is the package, we can see that all these add, subtract, there's a referred to some states. So ALU add or sub is like the same thing. Wait. Yeah. Add is 0, add is subtract is 1. Okay, so this alright. So for this case, right. Okay, that's fun. And so once we do this, the ALU result is supposed to be stored, right? Assign 0 equal to ALU result is equal to all 0. Why do we do this? There's no write command here. Yeah, this is the write command. Default it is 0. Yeah, and I have a question. Why at the end everything is set to 0? Oh, okay. Why is it done though? Okay, so for branch instructions, you need this flag to whether to know the operation of your ALU is 0 or not. Okay, that's fine. Oh wow. So to check if the result is odd or even, we might need this last bit. That's actually very fascinating, right? There's a lot of stuff going on. Okay, so let's go to your ALU. Yeah, so you import this as usual. Why is it binary to hex? Okay, that's not for concern now. So let's go with this. Await timer for ALU control 0 for something in the range. Randomize SRC1, SRC2. Write the value of SRC1 to SRC1 value. Okay. Source 1, source 2 registers are filled. We expected to not take account for overflows. So expected SRC1 and so you multiply it by 1, but how does that mask it? Okay, I don't know the meaning of this. Yeah, there's a test case for each. So you set this value so that you know that it's for ALU and yeah, that makes sense. And SRC is any random value for you to 1,000 test cases. SRC1.value1. Okay, yeah, that's right. Expected is so you assert, you check whether this is equal to a result. Okay. That is simple. For practice, let's write another test bench that we want to write for, let's say, our case. I don't know why this test is written first. So this is like, yeah, where is this function? Oh wait, this is the syntax. Did we do this for memory? Oh yeah, we did. So we just have to write this test function. Okay, so they have done like a multiple functions. Okay, so we'll write one test bench. Let's finish this. Let's do one for add. Yeah, let's do one for add again. So this is, don't call it add test. Okay, that's alright. And design of the test, yes. We have the ALU timer, ALU control value. Okay, so for add, I think it's 000, right? And expected should be addition of both, and is equal to expected. Yeah, I think this should do it, right? It's so 70. Let's make this something we know. So 0x 0 0 1 1 2 3 4. Yeah, so output should be 2, right? Yeah, it should be 2. Yeah, let's make it. Wow, so all these tests passed. Oh, by the way, I think I did not initialize my test, right? It has to be in the main. dude, I did it again. Not the holy course. Okay, so yeah, my test is also passing. I did it for like 71 times. Oh, how many cases did I put? 70. It took 71 times because it waits somewhere. So if I just stop this, will it also wait? So many times, okay. Right, so the ALU is also tested. Yeah, I haven't done the other tests, but let's just go through them. So first things first is you test the addition. So for addition, this is the op code. Sorry, not the control code. ALU control code, that is 00 for addition. Then for addition and test, this is 0010, okay. And then for addition is the same. And then for OR test is OR is 0011. This all right. And then for sorry, which test is this? Subtraction. It's also 001. Yeah, that's correct. And for what is SLT? I don't know what SLT, SSL. Okay, let's see the meaning of these. XOR we know. What's the meaning of these? I think it is mentioned somewhere. Oh yeah, sorry, it's mentioned here. So sign what? Okay, I don't know what this is. Maybe I'll ask. Okay. Shift left local. That's nice. It is shifting left by shamped bits. Basically, this is good for bypassing some multiplication operations, because sometimes multiplication by 2 is like you shift to the left, or division by 2 is you shift to the right, something like that. So it's like making your computation easy. So these are those instructions. These are those operations. Yeah. Set less than signed. Okay, I don't know that one. Shift right logical. Okay, this is great. Less than unsigned. This is just a comparison operation. XOR. Yeah, very necessary. Shift right arithmetic. Okay, so this preserves the sign for signed values. Interpret SRC1. Okay, so I don't have to worry much about these. So far it's good. Yeah, sorry. Yeah, so the ALU is done, which on a superficial scale, but yeah, I have a good idea of it. It's been 4.5 hours. Okay. Which on a superficial scale, but yeah, I have a good idea of it. Okay, so for verification, yeah, we did it. Okay, now what is a sign extender? I don't know what a sign extender is, so maybe I'm gonna check something about it mentioned here. Okay, so from what I understand is that there are numbers like 12 bits numbers, or like immediate is always 12 bits. So let's say there's a negative 8 or something. So that if we put it in 32 bits, it's going to represent differently because the sign bit is at a very is an MSB, is at the MSB side. So the sign extender will sort of take the 12 bits and represent it as -12 but in 32-bit format. So that's what the sign extender is going to do. If you look at the architecture again, yeah, if you look at the architecture again, you take the immediate numbers. So this is the controller for the ALU to send the ALU control signal. Yeah, and also, wait, what was I thinking about? This is funny. Yeah, I'm lost in the. Wait, what? I forgot about what I was thinking. The sign extender. Yeah, so the sign extender is. Yeah, this is the operation. But what? Yeah, it will take and output into the. Okay, so it should take a source number from the immediate section. So where's the immediate section? Yeah, wait, just a second. The sign extender is here. Okay, I've lost my chain of thought. Okay. Okay. Right, so the raw source is a 12-bit number. I don't know why is it made 24 bits. It should not be 24 bits, right? Yeah, it should not be out of the. It should be 12 bit, right? Because the immediate. Yeah, the output is 32 bits because we sign extended. Yeah, this is a bit confusing, but hold on, we will understand. So the first thing is the input logic is 25-bit SRC. This is directly part of instruction word where different bits form different types of immediate. Okay, immediate is immediate is okay, so why is it 25 bits? This is actually part of an instruction word where different bits form different immediate. Okay, I don't know what this means, but let's hold on to it. So 2-bit control signal that tells you what type of immediate we are dealing with. So I tag, S tag, etc. and RiscV tag. Okay, yeah, this is something I can understand. So what type of instruction set? Hi, Tejas. So for robotics, right now robotics is moving more towards the software side, and the hardware side is also moving. The mechanical side seems to be a bit same because there are less innovations. I don't know. I'm sorry. I don't know about that. But in short terms, robotics is looking good for EC students to get in. Algorithmic software for robotics is quite good. It's like an integration, like EC is also like towards a bit more computer. So if you want to go in robotics, I would say algorithmic is a good thing to get on now. People are also trying to make multimodal AI, which is like it takes sensor input, vision input, LLM input, everything it takes and makes just like one analysis. So multimodal AI in robotics is a good thing. I'm not an expertise to give you a roadmap, but these are just my suggestions. Okay, yes, coming on with the this. Yeah, so you have 25-bit. Okay, let's ignore that for now. So where is it mentioned that logic? Where is it mentioned that immediate is 12-bit? It's not even mentioned, right? Yeah, where is this line? I don't see this line. Okay, which code have I entered in this? Okay, it's this one. Okay, so this seems a bit weird. Okay, this makes sense. For immediate type, which is 12-bit. Yeah. Okay. Uh, so for this section of IAM source, this is like a 3-bit value, which tells you this is for immediate, this is for S type, B type, branch type, jump type. Just forgot all these different types. But yeah, I'm just gonna put it in ChatGPT and let me explain. So 20 to 24 is something else, and 13 to 24 is something else. Yeah, that's the sign bit. Why there is 20 mentioned there? Okay. Um, and 24 is the sign bit. Okay. No, you replace 24 with 13, right? Yeah, that's what you do. So that you have the sign. Sorry, you replace the 12 by 13. Okay, it seems I need to read a lot about these type of instructions to actually understand this fully. But I'm just gonna learn the immediate type because I think if I know that, maybe I can decode the others. So explain this in that. Hey, hi, I'll go basket. So let's zoom in on this line. Alright. So what this means, take a 12-bit image from the instruction bits, treat it as a sign number, give it 2's complement, extend it to 32 bits while preserving its value. So we're going from, yeah, this is what we're doing, yes. So raw SRC is 25 bits, so 0 to 24. 13 to 12 selects 12 bits. Bit 24 becomes immediate 11, that is the, 11 is the MSB sign bit, and 13 becomes immediate 0 LSB. So immediate bit 11 sign bit. Yeah, Tejas, if you're looking in terms of job perspective, just put your projects out in GitHub and make a video of it and hope that it reaches the right audience. And also for your application that you put for like a resume, you can mention that. I'm not sure if that's like if there are really great jobs in India for robotics, but also there are really great companies which are doing a lot of good work. So and a lot of people are looking at India to outsource their work. So it's actually a good time. ROS is good. ROS is like the framework that everyone uses, so you should not have a problem. Yeah, I'm not sure if it would be enough for to get a job because it matters a lot on contacts and the way you can build it by publishing your work and getting recognized. So yeah, that's my suggestion. Yeah, sure, no worries. Okay, IM12 is equal to raw. Extract the 12-bit immediate. That's from 13 to 24. Okay, SignExt then 12 to 32 bits. So what do you mean by this? So SignExt then, yeah, 11 is the sign bit. Immediate is equal to 20 times. Okay, so with this instruction, first is your immediate bit, that is your -12, which is gonna be here. Then source register's address x5 is 5-bit only, it's here. Then function 3, this is your opcode, so you're doing an addition, right? So maybe this will be addition for 0 to 000, or like 4 times 0, oh no, it's 3 bits, so it's 4 times 0. Output is a machine instruction code. That's going to be an user destination register. Okay, so we did this in the decimal. Okay, this is if you take a 2's complement. This is the scenario, right, for 12-bit binary. So this is -12. So when you map it to raw SRC, so this contains like immediate is first. So this is the first 24. This is 32 bits, right? Like 12 plus 4, it's 18. 18 plus 3, 21. Then you have 10. Yeah, it's 32 bits here. Of course, all the instructions are 32 bits. And if you map, okay, so how come for this section, raw SRC contains a 12-bit immediate? Okay, this thing contains a 12-bit immediate, which I don't know about. So the 24 is the signed bit, right? Like this is the signed bit. Yeah, and these are the rest of the bits. So yeah, these are the rest of them. So sign extension. So immediate, take the sign bit that is 24, repeat it 20 times. Okay, concatenate with 12-bit immediate. Okay, and resulting in, okay, so this is, okay, so this is what it's doing. So yeah, when you do 2's complement, you have 1, 1, 1, 1, 1 in the number. So how is 12-bit represented? 12 is like, yeah, let me just. So 1, 0, 9, 10. Yeah, 1, 1, 0, 0 is your 12, and to make it a signed bit, when it's 12-bit, so 12 as in 4 3s are 12, right? So 0, 0, 0, 0, 0, 0, then 1, 1, 0. Yeah, so let's hope. So basically, if I were to explain here, So this is your 12, which is 0, 0, 0, and 0, 0, 0, and 1, 1, 0, 0. Yeah, this is your 12. And then if you want to take minus 12, you take a 2's complement, right? Yeah, wow, this, sorry, the chat thing did it, but this is what you get. You basically, you add 1 to this, like basically you do this minus 1 or something, and that basically gives you a 2's complement, if I'm not wrong. So this is your minus 12, and if we see what what here it means is that your this immediate is stored here, so you are concatenating this string, that is the sign number that is at the place of 24. So the 25th bit is your immediate, so the 25th bit, so the 25th bit here is your immediate. I don't know if it's structured the same way. Yeah, I think something else, like how is it structured? It must be a bit weird. So okay, so if I get it right, then yeah. Let's just assume for now. Let's not strain our brains. I think I'm in the right direction, but I get the logic behind this. So this is the 2's complement. You do, like, basically you have a 2's complement, then you do the sign extension for immediate type, and then for S type, B type, J type, U type. Basically, I need to know what is S, J. Okay, so immediate, yes, add I and I. Right, dude, you don't have to explain this much. These are the store instructions. Okay, yeah, and branch type. Yeah, branch if equal, branch if not equal, branch if less than, branch if greater than. Jump type, jump to label, right? Where is the label stored in? Yeah, I think the label is stored somewhere. Okay, so upper immediate, yes, yes. Okay, that's quite good. So we understood on a superficial level again, not in that level, which is not bad. Okay, then CD, this is the ALU, no, this is not an extension. So, yeah, we can check the test case. Well, the thing is, you have everything, but I'm just not that great at interpreting it right now. Maybe it will take me a bit of time, but this is good. Yeah, let's check the test bench once again. Yeah, so we have a test bench. It's quite small, right? Immediate 123 number. Then leave the room for random junk. Okay, source 0. So this is for the immediate instruction, I believe. No, what is this? Source is the instruction type. So this is immediate instruction type. 25 bits sent to the SignExt and contains data before. So this is maybe for the I type, S type, B type, J type, U type. Okay, this is quite a lot of work. Yep. All the instructions passed. The thing is that this takes such less time, right? The immediate. So this is a good indication to use this instruction, the immediate instruction, for like majority of work, so that there is less execution time. Or maybe it's just because there are like less samples. It seems like the samples are pretty much the same. Oh no, there are, sorry. Yeah, there's a for loop here. Yeah, of course, yeah. Okay, that's good enough. Okay, so far so good. Let's go to the basic control. Okay, my brain's sort of fogging. I need to take a break. Yeah, why don't we have to make a code for the program counter? So for the load word instruction, the opcode is 1 1. A register write is 1. Yeah, it's an immediate instruction. ALU. Yeah, for the ALU. No, there's nothing for the ALU, right? Why do you have to use the ALU? Memory write result SRC branch ALU operation 00. Yeah, what is ALU SRC and what is ALU 00? That's quite confusing. Yeah, let's just use the one with instruction I. How do we not make this full screen? Do we click here? Okay. Yeah, we just want the load, right? We don't want the ALU, we don't want the SU, RB, yeah, we don't want this. Okay, so this is good work. For now, I can see I can build a picture for the next step. But I'm afraid I have to end the live stream here because yeah, it's quite a long time and it's been 5 hours. My brain is a bit cooked. I need to take a bit of rest. Maybe I'll start soon, but yeah. Thank you so much, guys, for being a part of this. To have whoever who joined, it was great to have you guys here. I will do another series. There will be a final video where I do a sort of summary of the entire project. Hopefully, if I'm able to complete it. There's a lot of things going on, but hopefully I should be. So yes, thank you so much for being in the live stream. I am going to end it right now. Thank you so much, guys. Have a nice day and a good week ahead. Yes, bye bye.